Now that we've talked about the different forces that are involved in the wind, we're ready to talk about wind systems. Each of these wind systems is going to apply some of the forces that we've talked about, but in some cases not all the forces discussed are used. There's two types of wind systems: large-scale wind systems and small-scale wind systems. With large-scale wind systems, winds travel a great distance, whereas smaller-scale wind systems, the winds don't travel very far. They're more localized. In this video, we're going to focus on the larger scale ones. When it comes to large-scale wind systems, there are two types: those that are in the upper levels and those that are at the surface. Let's start with the upper level ones. Upper level large-scale wind systems are called geostrophic winds. With geostrophic winds, there are two forces involved: pressure gradient force, because if you have a wind, you have to have a pressure gradient; Coriolis, because we're talking about winds that travel a great distance, so the rotation of the Earth matters. But in this case, there's no friction. The reason why there's no friction is because now we're talking about winds that are well above the surface. Because they're above the surface, there's nothing acting on them to slow them down. So what happens is you have pressure gradient force and Coriolis force balancing out over time. This leads to a relatively straight path wind that's parallel to the isobars. The figure to the right can help you visualize this. In this image, the white lines represent isobars, or lines of constant pressure. You can see there is an area of higher pressure and an area of lower pressure. Winds are going to want to go from high to low, which is the pressure gradient force, but Coriolis is going to balance out with that and deflect the winds perfectly to the right. The red arrow representing the wind, you'll notice, is parallel or in between those white line isobars. This, however, is a snapshot of geostrophic winds. We can also talk about how they get into this balance. That's where this image comes from. This image is very similar to the one at the top. There's areas of higher pressure and lower pressure. In this case, though, it's showing you how we got into balance. Each of those arrows represents something different. The brown arrow represents pressure gradient force, the blue arrow represents Coriolis, and the black arrow represents wind. If we go to our first time step all the way on the left, we have a pressure gradient. Because of this, air starts to move. But at this point, it's early on, and so the wind is quite weak, hence the small black arrow. Because the wind is weak, we actually have a weak Coriolis to the right of the wind. If you remember, Coriolis is a function of two things: latitude and wind speed. When wind speeds are lower, Coriolis is weaker. Now let's talk about time step 2. In this time step, the winds have increased in speed a little bit, denoted by the longer black arrow. And because of this, Coriolis has also increased a little, deflecting that wind a little bit more to the right. In time step 3, this continues. The wind speed has once again increased, leading to a stronger Coriolis, and the wind being deflected even more. Finally, we get to our last time step, and wind speed has increased further, and so the Coriolis arrow has also increased and deflected that wind perfectly to the right. And so in this final case, you'll notice that the pressure gradient force arrow and the Coriolis force arrow are in perfect balance with one another. The wind at this point will stop accelerating and go at a constant velocity and travel parallel to these isobars. The second type of large-scale wind system is a surface wind system. These surface wind systems we call ageostrophic winds. Often when you put the letter A in front of a word, it just means not, and that is the case here. Ageostrophic winds just simply mean not geostrophic. With ageostrophic winds, we have to worry about all three forces. Pressure gradient force, because again, to get wind, to initiate it, you have to have this force. Coriolis force, because it's still a large-scale wind. And then lastly, we now have to focus on friction. Because we're dealing with surface conditions, there's things on the surface such as trees and buildings and even people that are going to act to slow the winds down. What this does is the frictional force actually disrupts the balance that we saw with geostrophic winds. Because the wind speed decreases, Coriolis is going to be reduced, since again, Coriolis is a function of wind speed. Slower winds are not as easily deflected. And so what this leads to is winds that actually cross the isobar. So if you look at this figure, pretty similar to the one that we looked at for geostrophic winds, the wind arrow is no longer parallel with the isobars. It crosses them. That's because instead of being able to be perfectly deflected, it's only partially deflected due to this weaker Coriolis term, which resulted from slower winds. When it comes to surface ageostrophic winds, a lot of times we talk about specific wind systems. One of these wind systems is known as a cyclone. A cyclone is just the scientific word for a low pressure system. Low pressure systems actually spin counterclockwise in the northern hemisphere. You can see this in the diagram on the right. The pressure around this system is relatively high. The air is going to go from high pressure to the interior low pressure, but Coriolis is going to deflect it partially to the right. And so you end up with this pattern. These cyclones are often recognized for having active weather because of rising motion. So think about this, look back to the diagram. Those wind arrows are generally converging into the center. If we take a cross-sectional view and place the low at the surface, what's happening is these winds are colliding or converging, and so when they do this, they're not going to go underground, they actually go vertical. And this rising motion, as we found from atmospheric stability and parcel theory, is a key ingredient for clouds and precipitation. The other type of surface ageostrophic wind system is an anticyclone. Anticyclones are just scientific names for high-pressure systems. These high-pressure systems in the northern hemisphere actually rotate or spin clockwise. Again, imagine air going from this center high pressure to the surrounding outside lower pressure. As it does this, the winds are going to be deflected partially to the right because of Coriolis. Similar to what we did before, let's place a high-pressure system at the surface. In general, the winds are leaving this area of high pressure, and so something has to fill that void from the air diverging at the surface. And so what happens is wind from aloft or above sinks to replace that air. And so we end up with sinking motion, which, as we know from atmospheric stability and parcel theory, is the opposite of what is needed for clouds and precipitation to be produced.